Julie has over 100 publications and is a frequent invited speaker. Her research combines spintronics and novel devices for neuromorphic computing. So we are very lucky that she accepted, to also speak to us. She's a fellow of the American Physical Society, and she's been awarded the Jacques Herbrand Prize of the French Academy of Science. In 2013, she created an interdisciplinary research network, GDR Biocom, that is, general, and we should all check it out. The goal is to produce bio-inspired systems and promote it, and she chaired actually the network. In 2018, she received the silver medal of CNRS in physics for her pioneering work on spintronics and brain-inspired computing. She is the recipient of 2 prestigious ERC grants. The first one was NanoBrain project, memoristic artificial synapses and the integration neural networks from 2010 to 2015. And the BioSpinspired project, which was about bio-inspired spintor computing architectures between 2016 and 2021. And I think a big part of today's presentation will relate directly to this project. I've known Julie for many years, and we are all inspired by her work, and we are very happy to have her. So welcome, and now we give the chair to you so you can start presenting to us. I will suggest that everyone mutes their microphone and maybe even stop the video while we have the talk, and then we can start again. Okay, thank you very much. Let's mute and get started. Julie.
Okay, thank you very much, Christopheros, for the nice introduction. So yes, so in this talk, I would like to show you our recent progress towards building hardware deep neural networks with nanoscale spintronic oscillators as neurons. So of course, the motivation for this work are the very impressive recent progress in the field of artificial intelligence. As you know now, these neural networks in software, these software neural networks are able to perform some tasks even better than humans, like playing complex games like chess or poker or Go. And also, I really like this example that is very impressive. They can also generate new, completely new pics of pictures. These people do not exist, and you see the degree of realism. So these pictures were basically invented by neural networks, so it's very impressive. They are very realistic, but you can see that, for example, the earrings of the woman are not symmetrical. Can you see my pointer, by the way, here? Or?
Yes, we can see your pointer, yes.
Okay, great, thank you. All right, so the thing is that today, when these neural networks are trained on our computers, they're extremely power inefficient. That is because in a neural network, when you want to train them, you have to tune millions of parameters, and at each training step, so you can have millions of training steps, and at each training step you have to fetch these parameters in memory, and then you have to bring them to the processing, do some complex operation, put them back in memory. And so this data motion is sustained all the time during training, and this is what consumes inordinate amount of energy. And this makes these neural networks that are inspired from the brain orders of magnitude, like 3 or 5 orders of magnitude less energy efficient than the brain, and also way slower. And the reason for that is that in the brain, the structure is very different. You have the neurons and synapses that are totally entangled and closely connected to each other. And in fact, neurons are carrying, you can say in a rough way that neurons are carrying out the processing, and synapses are holding the memory. And because they are in close contact, you don't have the data motion all the time. the data in the synapse is directly available to the neurons. And this is why the networks are very fast, even though their individual components are slow. Neurons and synapses, they work at hundreds of hertz. Alice Mizrahi, in this paper here that we put recently on arXiv, has estimated that it has been shown that you need about 1,000 kilowatt per hours to multiply by hours to train a natural language processor. And this, in fact, you see corresponds to 6 years of full brain operation. So you can see really the difference in energy between the neural network and the brain. And so if we want to alleviate this problem, it means that we should try to go back to the structure of the brain to build hardware neural networks. And so for that, the main idea is the following, is to have really physical neurons represented by these circles here, connected by physical nanosynapses in a very dense way in a chip, like that, in order to go back to an architecture where memory is extremely close to processing. And so now this is really the trend in neuromorphic computing. Many people, there is a huge effort in the world to try to do that. Another challenge is that if you would like to make small systems like chips that contain like hundreds of millions of neurons and synapses, which is the standard for let's say, state-of-the-art image recognition neural network these days. If you would like to fit all these components in a chip of about 1 centimeter square, if you make the calculation, you find out that each device should be smaller than 1 micrometer square if you want a network that really runs fully in parallel. So it means that you would like to have neurons and synapses that have a nanoscale size. So it means that we need to invent these novel devices, these novel nanoneurons and nanosynapses. And for this, we need to look at which characteristic we need. In the brain, neurons emit spikes. So here you can see the electrical spikes of neurons. These spikes are weighted, let's say, are communicated to other neurons through synapses. And synapses are going to modify the strength with which these signals go to the next neuron. These signals are then weighted and arrive as a current on the membrane potential on the neuron. And this creates some fluctuation in the membrane potential of the neuron. And what you see here is this membrane potential as a function of time. And each time you have a spike, you see that the membrane potential increases a little bit, and then there is a leakage, so it starts to leak. But if there are enough spikes coming at a certain time, they accumulate, and when it reaches a threshold, there is a reset of the membrane potential, and the neuron emits a spike. So it means that if there is a regular trend of spike arriving to a neuron, it's going to be regularly excited and is going to spike in this regular manner. So you can see this as a non-linear oscillator, which takes a current as input and emits spikes at the output. And what is very important is this non-linearity, where here you see the spike frequency as a function of the current is non-linear. And this is key to computation, and this is what is imitated today in a hardware neural network. So most neural networks today are not imitating these features in software. They transform the trend of spike into a frequency that are some real values that are represented here by the x1, x5. They go through synaptic weights W, which are coefficients, which can be positive or negative. Then they are summed, and this weighted sum Y is injected into the neuron, and the neuron is nothing dynamical, it's just a mathematical function that is nonlinear, So it's typically this kind of rectified linear unit where you have the output of the neuron Z that is doesn't respond until a threshold where it reproduces the input. And so this is what is done in most neural networks today. And so you see that the input of the neuron Y is the weighted sum of the inputs of the outputs of the previous neurons multiplied by this weight, synaptic weights. And this operation, this sum, weighted sum, is called the multiply and accumulate operation. So it means that there are two main, there are, let's say, three main characteristics of the device that we need in your neural network. Neurons need to be nonlinear. Synapses need to memorize the weights. And ideally, there should be an easy way to implement this multiply and accumulate operation, because this done in CMOS is very complicated and takes a lot of area. Okay, and then there is another thing that is very important, is that you need multi-layers of neurons. So state-of-the-art neural networks are deep. They extract features layer by layer. So here, for example, you see an example of a deep network where you have the layers of neurons. You see that there can be in current neural networks, there can be up to hundreds layers of neurons. Here you have images, pixels are sent to the inputs. And what is interesting is that you can see that layer after layer, the neural network extracts features that are more and more high level. So at the beginning is going to learn only make some edge detection, then recognize some feature of faces, and finally at the output is going to really identify faces. So the power of neural networks today really comes from this deep architecture. So how are these networks trained? This is done through the backpropagation of error. So this is also a source of their power. What happens is that you typically apply an image that you want to recognize at the beginning, for example, so in these input units. And then the information is going to propagate through the networks, and then you get some output here. And at the beginning, all the weights in the network are random. So the output is not going to be the one you desire. So the training data is labeled, so you know what is inside the image, if it's a dog or a cat. And so you can compute an error. And what is really very powerful is that there is a way then to modify a little bit each of these weights so that it is corrected by its error to the final output. This is what is written here. You see that each weight delta W has the adjustment of the weight is going to be its contribution to the error to the output. And the way to do that is called backpropagation of error. So you can, the idea is to compute this quantity by looking at the error at the output and then backpropagating, doing some chain rule of derivative to get back to this quantity. And what you can see from this graph is that this computation actually is very numerical intensive. So it's not at all physical. It requires many steps of derivation. It requires to store some gradients, apply them, sum them, etc. And so the challenges of neuromorphic computing today are to fabricate optimized hardware synapses and neurons, to integrate in these networks, to build deep networks. And so this means having these different layers of neurons and synapses, and it means to be able to implement this successive multiply and accumulate operation, and also to find smart ways to implement backpropagation, which is really, really one of the main challenges today neural networks. So there are many ways to implement this kind of hardware neural networks. People are really investigating today which one is the best. There are many options, many kind of devices and materials that you can use. So you can use phase change material, ferroelectrics, optics, organics, resistive switching RAMs with filamentary switching. There are many, many options, but today in my talk, I will focus on Spintronics neural nets. So why are we interested in Spintronics? Well, this is because it's really a toolbox for neuromorphic computing. The idea is that Spintronics is highly multifunctional, and using similar materials and devices, we are going to be able to design different response functions and obtain different nano devices that can play the roles of synapses or neurons and even interact together to compute. So the building block of Spintronics is the magnetic tunnel junction, where you have these two magnets separated by a thin insulator layer here. So I don't know if everybody here is a specialist of Spintronics, but just in case, so in these elements, that can be really nanoscale. The magnetizations of the two layers can point parallel or anti-parallel. And depending on this state of magnetization, the resistance of the device is going to be very different. And so this enables storing a 0 or a 1 and to implement a binary memory. And in order to change the state of this memory, the idea is to send a current through this small pillar that can be either positive or negative. And by changing this current, you can reverse the state of the memory. And of course, what is very important is that these devices can be scaled down to 10 nanometer, and they can be integrated in a regular CMOS process. And so there's been huge progress recently, and all the major foundries are now integrating these devices in their commercial process. So this means that we are going to in the next year, see chips that integrate massively the devices. There are already demonstrators of memories with billions of magnetic tunnel junctions, gigabits memories. So this shows that spintronic nano devices have this memory capacity that is crucial for synapses, but further than that, and also that they can be built in huge number and connected to standard electronics. But also, what is interesting is that we can go beyond this device by changing the structure of these magnetic tunnel junctions and changing the materials that we use. We can actually engineer different response than just this binary switch. We can implement stochastic oscillators that are going to fluctuate with very low energy due to thermal fluctuations. So this can be a random number generator. By using magnetic textures, we can also have multi-level states of resistance. So we can make memristors. There are, of course, you are working on skyrmions, so that are also very interesting for this purpose. And so it's really a very interesting toolbox to implement all the functions of neuromorphic. So in my talk today, I'm going to focus on one very specific device that we are interested in, which are spintronic nano-oscillators. I'm going to show you why we think these spintronic nano-oscillators are very interesting to use as neurons, and how we are trying to progress toward making deep neural networks with these devices. So these spintronic nano-oscillators, they are essentially magnetic tunnel junctions, but they are used in a different modes than the memory. Instead of sending short pulses of currents, positive or negative, to switch the magnetization, the current is applied in a sustained way to the device. And so what happens in that case is that when the current goes through the first magnetic layer here, that is in general fixed, it gets spin polarized, and so the electrons are carrying some spin, and when they impinge on the top layer, this spin is transferred to the magnetization, and it can generate a sustained motion of this magnetization. And so because these are magneto-resistive devices, when we measure the voltage across these junctions, we see an oscillating voltage. These are experiments, by the way, so you see it's very clean. And there are two features that are interesting. First, the time scale. So you see here that these oscillations occur on the time scale of nanoseconds. So here, what I'm going to show all the experiments are going to show are done with vortex oscillators. So these ones are rather large, and their base frequency is about hundreds of megahertz. But by choosing different size of junctions, different materials, different thickness of these magnetic layers, this frequency can be largely tuned between tens of megahertz to several dozens of gigahertz. Okay, so what it means, okay, and so what is important also is that, so you send a DC current and you get an oscillating output. So this is a nonlinear oscillator. And the second very important thing is that the response is nonlinear. So here what I'm showing is the emitted power, so microwave power, which corresponds to the square of these oscillations as a function of the input DC current. And you see that because there is a threshold current to excite the magnetization, first the emitted power is 0, and then it increases linearly with the DC current, because the more DC current you put, the larger the orbit and also the larger the power. And so you have here a rectified linear unit, like in neural networks today. So we could use that as a neural net, as a neuron, a nanoneuron. But what is particularly interesting, you see, is that you send a DC current, you apply this nice non-linearity on it, something that you really would like in a neural network. But even more interesting, this processed information is then converted into a microwave voltage. So it's like a radio neuron, right? A radio frequency neuron. It takes an input, performs the operation of a neuron, and then can potentially broadcast these outputs to other neurons. And so the questions we ask ourselves is, okay, could we use this to build deep neural networks where neurons communicate with each other through these radio frequency signals? And could we use that to connect a huge number of neurons together? Could we increase the connectivity of the neural networks? And also, because these neurons are very fast, could we improve their speed? So we are experimental physics lab. So we needed to go step by step and demonstrate function after function. And so the first step was for us to say, okay, but these are nano devices. So as every nano device, because of their small volume, they can be sensitive to noise, they can drift. So are they going to be good enough to achieve some neuromorphic computation? So we wanted to investigate that. So what we did is that we took one single junction and we used it to emulate a full neural network of 400 neurons by using the same junction to play the role of each neuron one after the other. And so basically we used a scheme of time multiplexing and a framework that is called reservoir computing to emulate a neural network. And so what we did is that the signals that we processed were words pronounced by different speakers, digits from 0 to 9 pronounced by different speakers. They were pre-processed, accelerated to be sent to these to our oscillators, and then the output was also pre-processed because these are just the neuron. We didn't have the final synapses. But what is important is that what we showed is that experimentally, this magnetic tunnel junction was good enough, stable enough, and had enough rich dynamics to recognize these spoken digits with a success rate over 99.6%, which is similar to what is done with much larger hardware neuron, and also similar to what is done in software. So it really proved the interest of these devices for neuromorphic computing. Then the second step that we performed is to use these devices to implement a single layer neural network. So what we did is that we connected 3 oscillators in this way here, in a line. And we wanted to show that we could use them as a neural network, as a single layer neural network. And so what we did is that we showed that we can recognize patterns through the mutual synchronization of these oscillators. So what's happening here, you see that through this connection scheme here, we can send a different DC current through each oscillator. So it means that we can, I forgot to say, but so it means that we can control the frequency of each oscillator independently, because the larger the current through each oscillator, the larger the frequency in our devices. So we can control their frequency. And also you see that here, because each oscillator emits the microwave voltage, these microwave voltages are going to propagate through this line. So it means that each oscillator is fed by a DC current, but also receives the microwave emissions from the other oscillator. And this can influence their dynamics, and it can synchronize the oscillators, even if they have different frequencies. So what is shown here in these 2 graphs is a case where the oscillators are, let's say, disconnected. So you see they don't feel each other, they are running independently, and so you see the peak of the 3 oscillators. There are microwave emissions, so there are different frequencies, oscillator 1, oscillator 2, oscillator 3. So they emit a microwave power, and then when we connect them together, you see that because they interact together, if their frequency are close enough, here in a range of 5 megahertz, well, they can synchronize. And when they synchronize, you see that they gain some coherence, and also you have constructive interference that result in this very large, much larger microwave power, and also much thinner. And so you see that this kind of effect could be used as a detection. So for example, if the oscillator receive signals that if you want to do some pattern recognition, this kind of behavior of the oscillator could mean that they do not recognize the input pattern, whereas if you get this output, it means, oh, we recognize the input pattern. So that's a way to perform binary classification. And so we wanted to show that. So we designed a toy task for the oscillator, which was to bind some temporal data. So let me try to explain you. So this is really completely made up task. So we consider a fictitious mouse with only 3 neurons. And we say that this mouse is going to be presented with some different kind of cheese. And depending on the kind of cheese that it smells, the neurons are going to spike differently. So each neuron, we are going to consider that each neuron emits only 1 spike. And so that, for example, if the cheese is cheddar, the neurons are going to spike with this kind of sequence, this kind of separation between the spikes. So black, red, and blue for 1, 2, and 3. But if it's a different kind of cheese, the spike of the neuron will be different. So for example, this kind of pattern for Cheshire. And so this is, so you see we considered 4 kinds of cheese: Cheshire, Brie, Stilton, and Cheddar. And we consider that the first neuron always spikes at t equals 0. And so what we represent on these axes are the times t2 and t3 of the second spike, of the second neuron and spike of the third neuron. Okay, so this makes some kind of toy database, and our goal is to see if we can train our oscillators to recognize which cheese is presented to the mouse, depending on the timing of the spikes. So how did we proceed? We used an algorithm that was proposed by Hopfield, that is in this paper, that is really inspired from neuroscience. So his idea was to say, well, when you want to recognize spiking temporal data through using synchronization, what you can do is that each time you have a spike, you start to ramp the frequency in the corresponding neuron. So you see, if I have neuron 1 spiking, then I start to change its frequency linearly with time. Okay, so this is oscillator 1, neuron 1, oscillator 1. So I start to, and when the second neuron spikes, I'm going to start changing the frequency in oscillator 2. And when the third neuron spikes, changing the frequency in oscillator 3. Okay, and so here you see that for the spikes of Cheshire, we have chosen a case where the ramps are chosen so that the frequency of the oscillators never come close to each other. And so they are never going to synchronize all together. On the contrary, if we choose the ramps smartly, when the spikes arrive in the order and timings corresponding to Cheddar, the ramps are going to converge at a given point, and this is going to give rise to a synchronization of the oscillators. So if I sum up, let's say using this scheme, you see we want to be able to recognize Cheddar. What we are going to do is that we are going to train these ramps slopes so that every time a Cheddar pattern is presented, the ramps do converge at some point and the oscillators synchronize. And the training should be done so that if it's another kind of cheese that is presented, the ramps never converge. And so there is no synchronization even. Okay, and so this is what we have done experimentally. So we have found with very simple learning rules that we mostly searching by hand the good manually, I mean, using very simple algebraic consideration, which ramps would work. So here you see we want this network of 3 oscillators to recognize Cheddar. And so we have found some ramps, and we have applied them to the oscillators. And so here you see the currents applied to the oscillator, because the current ramp through the oscillator corresponds to a frequency ramp to the oscillators. And you see the ramps applied when you have Cheddar, Cheshire, Brie, and Stilton. And here what you see are, so these are the DC currents injected in the oscillators, and these are the frequency of the oscillator measured on the spectrum analyzer. So the colors here represent the microwave power of the oscillator. So you see there are three traces corresponding to the 3 oscillators. And what is important to notice here is that on these graphs, you see it's very red here when the ramps converge, because the power becomes very strong due to the synchronization of the oscillator. And so when we plot the integrated power of the 3 oscillators as a function of time, you see that when it was Cheddar that was presented to the oscillators, we obtained indeed a very large power that has this shape. Whereas when it was the other cheese, because the ramps never really converge, the frequency of the oscillators do not meet at the same time, and so we stay with a low power. And so we can put a threshold and to say now, if we obtained an integrated power that is above this threshold, it means that the oscillators recognize Cheddar, but if it's below this threshold, it means it's another cheese. Okay? And so we did these experiments and so in hardware, and we have shown that we could, our small networks of 3 oscillator was able to recognize Cheddar with a success rate of 97.5%. And then we could retrain the oscillators to recognize a different other kind of cheese. And these are the results here. And overall, we obtain a success rate for the oscillator of 94%, which is quite good. And so in order to compare this result to something, what we did here, so you see, this is this point here in orange, these are the oscillator experiments. What we did is that we have compared this to the result with a simple perceptron, and also we have performed some simulation of oscillators without noise, and you see that the results are very comparable. Also, what we have done is that we have changed the database, so we have increased the jitter in the spike timing to see how robust the network was, and you see that overall the experimental neural network for small, well, I mean, for let's say medium noise in the spikes of the database is doing better than the perceptron, but overall is give very similar results. And so even though our learning rule is very simple, and so probably we could achieve better results by having a nicer, more automatic, refined rule to adjust the ramps of the oscillators. And so what this result shows is that we can use this mutual synchronization of the oscillators, so they are non-linear dynamics, to recognize some patterns, here some temporal patterns, and also it shows that we were able to make a single layer neural network, so a kind of perceptron. Okay, but of course we want to go beyond that, and we would like to make a multi-layer neural network. So the third step was to build a 2-layer neural network. And so in order to do that, what we did in this scheme is that we used 4 nano-oscillators this time that were connected in the same way as I presented earlier on here. And we have emulated a first layer of neuron by using microwave sources. Okay, and so these are lab equipments that were sending microwaves into a strip line that was placed just above the 4 oscillators. You can see the SEM pictures here. So like we had a strip line 300 nanometer above the oscillators. And so we had 2 microwave sources, so they were playing the role of these 2 neurons here. And we sent some signals. So we encoded in the frequencies of this source, we encoded spoken vowels. And so what we have shown is that we could recognize the vowels by looking at which oscillators in the second layer was phase locking to the microwave source in the first layer. Okay, and we were able to train the oscillators to do that by changing the current through the oscillator. So basically, it was the first idea on how we could propagate the information layer by layer, right? And so what you see here is a case where normally when we don't have inputs, because we have 4 oscillators in the microwave spectrum, there are 4 peaks of emitted power. But here, because we have the 2 inputs, you can see that the spectrum was modified, and the 4th peak has disappeared because the oscillator has synchronized phase locked to microwave source. Okay, And so this is how we were able to recognize the vowel. And so this was nice. And so a way to represent this way of performing recognition is shown here. So you have each color here, each region of color is a different synchronization configuration. And here the different vowels you see are contained in the different regions, in different regions of different colors, which correspond to their classification. And one thing that is very important, you see that here what we did is that we sent the microwaves directly above the oscillators. So there are some synapses, let's say, because there is some communication, but these synapses are fixed. In order to train the neurons, we change the DC currents for the neurons. So we don't have trainable synapses. And you see that because of that, this classification scheme is very rigid. It looks like a chessboard. It's not going to be able to classify complex patterns. If we want to classify complex patterns, like for example with this shape, this heart shape, you need to draw complex contours, and this requires to have trainable plastic synapse. Okay, and so it means that we need trainable synapses and MAC operations to build deep networks. And so we thought, how can we do that? And so you see that for the neurons, so for the oscillator, we put a DC current and we emit an RF current, okay? And it's going to be the same in the next layer. And so we thought if we want to make synapses between these oscillators, we need synapses that convert the RF output to a DC output, okay? And so what I'm going to show you is our ideas to do that, and this is the work of Nathan Leroux, Daniela Markovic, and Alice Mizrahi. And so how can we do to convert RF to DC? Well, what is very interesting is that in magnetic tunnel junctions, there is an effect that is called the spin-diode effect that does exactly this operation. Okay, so using exactly the same device as the neurons, but instead of sending a DC current, you send an RF current. What's going to happen is that if the RF current that you send is close to the resonance frequency of this magnetic tunnel junction, due to the spin torque effect, you're going to excite, if you are close to the resonance, large angle precessions. So here you can see the amplitude. So, okay, so what I'm going to show now are simulations. So you see simulation of the amplitude of the resonance. And if we plot the DC voltage across the device, it has a more complex shape because it's the multiplication of the RF input by the response of the resistance of the device. It's going to have this kind of shape. You see, you have a DC response that is small here, goes to 0 at infinite, and close to resonance is 0. All right, and what is interesting is that here, so you see that indeed there is a conversion from RF to DC, and also what is interesting is that in this region, the response is very linear. And we want to use this effect as a synapse. So how can we do that? Well, what a synaptic weight is doing is that it multiplies an input by its weight to get the output, okay? And so you see that when we increase the input RF power in the magnetic tunnel junction, the DC output will be larger and larger. So it means that the voltage is proportional to the input RF signal. And also, you see it's very linear in this region. Oh, yes. And what did I want to? Yes, and so when you change the frequency, you are going to be able to change the slope here. So here, what I'm showing is how V depends on the power for a given frequency of the junction, of given resonance frequency of the junction. And when we change this resonance frequency, you see that we can really change the slope here. And so it means actually that the output DC voltage is a multiplication in this range, is a multiplication of the input RF power by the difference between the input frequency and the resonance frequency of the junction, okay? So here, it means that for this kind of synapse, the input is a microwave power coming to the synapse, and the weight is the difference between the input frequency and the resonance frequency of this junction. Okay, and what is really nice is that for this kind of synapse, we can use exactly the same junction as neurons. They are just used in a different way. So how can we make a multiply and accumulate operation? Again, the idea is very simple. So we are going to simply put these synaptic junctions in series, okay? And we are going to give them different resonance frequencies, which we can do by changing their diameter or the thickness of the free layer, okay? And so the signals that come from the microwave power is coming from neurons before, okay? And they are going to have very different frequencies. And so the idea is to match the frequency of the neurons in the pre-layer to the frequency of the spin-diode synapse. So you see that we are going to choose the frequency of this synapse so that it's close to the frequency of this neuron, the frequency of this synapse so that it's close to F2, and this one close to F3. So that this synapse talks only to this neuron, this one only to this one, and this one to this one, even if we send all these microwave powers are multiplexed and sent through the same line, okay? And you see that if we do that, naturally, just through because voltages are going to add up, the voltage here across this junction is going to be the weighted sum of the microwave power by these synaptic weights. And so this is a simulation here that shows how it would happen. So in order to avoid some kind of background signal, we put the actually junctions head to head. And so that's why you have one that is positive, one that is negative, positive, negative. So this is how it would look like. And so what we have done through simulations recently is that we have, okay, so these, as we have seen in the neural networks that I've shown previously, magnetic tunnel junctions have non-linearities. And so in particular, the resonance frequency of a junction is going to depend on the input microwave power. So it means that in a way, the weight is going to slightly depend on the input power. And normally this is not something you want in a synapse. You want it to be perfectly linear, but all kinds of devices have some non-linearity. So here in this simulation, they include the non-linearity. So you see that here the color is the microwave power, and you see that the frequency indeed is shifting with the microwave power, and that this is not perfectly symmetrical. But we have shown that there are actually, despite this, there are ways to achieve very good multiply and accumulate operation. So here you see the simulated case with 3 synaptic spin-diode junctions as a function of the ideal Mach. So in black, blue is the ideal, and in black are the results of the simulation. And so we obtain a very good result. And so using this scheme, we have performed some simulations. So we have simulated a perceptron again, this time. So, but we have done a real task. So what we did is that we have as input the digits database where you have handwritten digits. So each image has 64 pixels, and there are 10 digits. So we have 64 synapses, and we have 10 output neurons, 10 outputs, okay? So here you can see the 64 spin diodes signals that correspond to the signal across one of these chains. And So what we have done is that we have trained this network through backpropagation. And here you see the difference between this resonator neural network, this spin-diode neural network with all the non-linearities and defects. And in blue, you have a regular neural network, and you see that we achieve a very nice recognition rate despite the non-linearity, up to 99 point something. So we have good results. Okay, and so what these results show is that the MAC operation is working, and also it means that we now, in principle, we can cascade, we can start to build multi-layer neural network by having neurons that convert DC to RF, send them to synapses that convert RF to DC through the MAC operation, and again go back to spin torque nano-oscillator. Using that scheme, we think we could build deep networks with very high density that communicates through radio frequencies. And this things is in progress in terms of simulations and experiments. And so the conclusion of a talk is always, and to come back to the introduction, so as we have seen, the challenges of neuromorphic today are to fabricate optimized synapses and neurons, to build deep networks with successive MAC operations, and to implement backpropagation. And in fact, we have developed solutions to these challenges from spintronic neural networks. And we are eager to like everybody, to go back to the lab to try to show that experimentally. So thank you very much for your attention.
Thank you very much, Julie. Thank you very much for a very, very, very impressive talk. We will open the session for questions. If, again, questions, either write in the chat and I can ask the question, or raise the hand with the reaction functionality of Zoom and you can speak directly. So, Julie, we were hoping for, 10-15 minutes of question time, if your time allows.
Yes, I'm sorry, I was over time. No, for me it's okay, but it's more for you. I'm sorry.
No, it's for us. It's it is great that you took more time to show us even more interesting things. Okay, so we will start with the questions. I will ask something to give everybody the chance to gather their thoughts. A bit of a general / generic question. I think there is the understanding that there used to be a divide of deep learning approach versus more biomimetic / neuromorphic approaches. Of course, even deep learning neural networks are inspired from how the brain works. My question to you is, do you think these two worlds are converging, or in order to achieve true intelligence, how close should the connection be with brain-inspired and biomimetic?
Yes, it's a very good question. I think, yes, so how to answer? Well, I can, what I find very fascinating these days is that the pioneers of artificial intelligence, who really invented deep neural networks, they were really motivated by the brain, understanding how the brain is working, and they say, okay, well, the success of our neural networks is due to the deep, well, they are deep, but also to backpropagation. And so they always say, backpropagation in a way must be implemented in the brain. And so now, and people were saying, well, it really doesn't seem like it's possible, because you see it's very numerical. There is no, how could this be done by synapses and neuron? And what is interesting is that in these last 2 years, there are starting to be really ideas between AI and neuroscience, how this could be done in the brain. I think it's a great source of inspiration for us, for neuromorphic computing. So these fields are converging, I think.
You think they're converging? Okay, so we will continue being inspired from neuroscience then, from the sound of it.
Yeah.
Okay, so let's see. Anybody wants to ask a question? Let me check the chat or any raise of hands. Is there something I'm not seeing?
Yes, well, I did raise my hand, Christophorus.
Oh my God, I didn't see it. Apologies. Okay, Tom, please ask the question.
Yeah. First of all, Julie, thanks for an excellent talk, which really covered the field very well. And particularly your last comment is one that I think resonates with a lot of people. What do you think the minimum power output you need as you scale these things down is likely to be?
Yeah, so yeah, it's a very important question. So I think that when you scale them, you can the power is typically we can expect is 1 microwatt, the minimum power. 1 microwatt, and then of course, if we want, there is a power, but there is also the energy that is important, and it's going to be important to raise their frequency, right? So
yes.
if we are at gigahertz or tens of gigahertz, we can really be low energy.
Yeah. Okay. No, I agree. I think it's a very important, interesting, and sort of exciting area to have a go at. But it's also I think a certain amount of work is going to be needed in that respect. The other thing is with the oscillators, what's the constraint, or what's the sort of ideal damping that you think would be best for this? So I suspect it's a little bit different to other applications of STOs.
Yeah, it's true. It's a very good question. So for example here. Yeah, so it's a good question. We are still thinking about it. So we've been playing with the parameters. So here in the simulation, in the end, we took the very standard numbers that everybody is using, -2.
Yeah.
If we want to stack in a given range of frequency, the smallest the damping, the more we can put synapses in a range of frequency, because we multiplex in frequency. So you see, for example, on this graph, can you see? Yeah.
Yeah.
Yes, you see that if the damping is very small, we're going to be able to put more of these diode signals in a given range. So this could possibly increase the number of synapses that you can connect per neuron.
Right, okay. I guess the reason I was asking the question is it occurred to me that you're using the real part of the complex permeability here,
yes.
effectively. And actually, if you increase the damping, which in many ways is the easier thing, you would actually, or that you would maintain your linear slope, but you would spread it over a larger frequency range.
Yes, exactly. Yeah, absolutely. So that's why there is some kind of compromise to make here, and it's something we need to figure out still. This is very new, so. Yeah,
because it might be that this is actually a little bit easier from that perspective than maybe some other things.
Yes.
Yeah,
so we are doing some experiments now, starting, and actually it's true that the damping is a bit larger, and it's helpful as a start, at least, because it's more linear on a larger range.
Yeah, exactly. Yes. Yeah. Okay. That's interesting. It's good that this experiment's going on to look at that, because that's an important area. Okay. Yeah. Thank you very much.
Thank you.
So we follow up with a question from, I see a raised hand from Ting. Ting is an academic at Manchester who is a machine learning researcher. So Ting, would you like to ask your question?
I cannot hear you, Ting. You're on mute.
Oh, sorry, I'm on mute. Yeah.
Okay.
Yes. Thank you very much for the talk. It's very interesting. It's very interesting for me to see how pattern recognition is done in a different way, in a different perspective. It's very interesting. So my question is about your slide 29, and so that's quite interesting experiment to do digital recognition. So here is how do you do the backpropagation here?
Yeah, so I skipped a lot of details. So what we do is that the pixels are converted to microwave power, that to the spin-diode synapses, and so what we so these devices have some non-idealities. So what we do is that we, in the forward pass, we really take into account all the device imperfections, but then for the backward pass, we compute gradients with ideal characteristics. Okay, and so that's because it really speeds up the process, and so that's how we. And so we use really standard backprop on the backward pass. And so this is done with PyTorch. And basically what we do in PyTorch is that we really, you see, have these characteristics. I mean, in PyTorch, basically, we really have this kind of response.
Okay, so you kind of do an approximation of this in a standard neural network fashion, and do backpropagation there and transfer the weight to this setup.
Yeah, so this is a simulation, but we tried. So it's not an experiment, but we really tried to be close to experiments.
Okay, and just to ask about backpropagation for curiosity, have you tried, are you aware of any non-standard backpropagation that has been developed specifically for a type of a nano device, just to suit the property of that specific device and develop new backpropagation kind of scheme? Is there any work like this?
So there is a lot of work. So because people have been really working a lot on memory stiff synapses. I don't know if you heard about this. In this context, people have been also working a lot on how to alleviate non-idealities of these devices and still achieve gradient descent with good quality, which is complicated. And so there is a lot of work in this area. And here we had to develop this kind of thing ourselves for our new kind of device. And we were happy to see that we could find a way to do it with high success, actually, by some calibration procedure and by using this different gradients in the backward pass.
Okay, thank you.
So we have another question from Yuli, who is one of our students working on schemionics. It's a really good talk. Thanks a lot, Yuli. The question is, if the frequency is improved to the gigahertz range, is there a new phenomena or much better performance that we could expect? In other words, is the frequency a bottleneck for the implementation of the synapses?
So I'm not sure how to answer this question. So you see that here we are using frequency multiplexing. So if we use a larger range of frequency, we can have more synapses, let's say. So this is an important thing. Here you see we are in a range of hundreds of megahertz because we made simulation for samples that we want to use experimentally. We could go to gigahertz. I don't think there is, it will have only advantages because we can speed up the networks and many people today are working on terahertz spin hole anti-ferromagnet oscillators, this kind of thing. It would be, if we could go to terahertz, we could even compute faster, so that would be really nice.
Which tool do you use for this? Do you use a tool, by the way, for the simulations, or is it something sort of? For
the simulations, we are using PyTorch.
PyTorch.
So, it's yeah.
Okay, good. So let me check if do we have any other question or any raised hand? If I'm missing something, please speak up. I do have a quick question about the fictitious mouse, which I really like. Yeah, I feel I need to comment that the fictitious mouse has a French palate and a liking for British cheese. So,
Yes.
so
the reason why I choose English cheese is because it was,
so, you know, I need to comment. Yeah. So okay. So on slide 17, of course, your later work already is sort of much more advanced on that. But I was wondering. I think you mentioned that when you ramp up, basically, when you combine the ramps in a way as to lead to the sync, I think you said you follow some hand-picked rules. So you hand-picked ways in order to combine them?
Yes, so we handpick, you see, in order to obtain convergence for one type of cheese and not for the other, you need to fine-tune the values of these slopes.
Mm-hmm.
And to do that, we use some very simple algebraic considerations, and then we adjusted a little bit. We tried by trial and error, and
okay.
and if we were able to convert that to something more like gradient descent on the slopes, I think we could really improve the results. But we didn't do that. Okay.
So, but you sort of envisage a way on how this would be sort of more systematic.
Yes, it can be done more systematic.
More systematic. Okay. Good.
I think Corey's got his hand up, Christophorus.
Okay, Corey. I don't see the hand up, but Corey. Yeah. Okay, I see. Now I see why I don't see it. It was hidden behind something else. Okay. So, Corey, would you like to ask a question?
Yes, I would. Thank you for the talk. Actually, most of the questions that I had were about the operation and the actual training process of the neurons, which have just been answered. But I've got one. So you have the DC to RF spin-torque oscillators as acting as the neurons, and then using them in reverse via the Mach operation, you have a synapse. Is there additional advantages to being able to have them simultaneously act as both? Because I know that a lot of the kind of mimicry of the how the brain works, people wanted to get that interconnectivity and the ability to change connections on the fly. Does that actually have a significant advantage when it comes to this, or would it be unnecessary to have that?
I think that because we use this frequency multiplexing, we can really avoid, we can really decrease the number of wires that are necessary to connect between layers. It's represented here. How can I say? So you see that because I don't have a good slide to really show that, but in between, you see here you have an output layer, okay? And what we do is that, yes, it's not represented as a one. Okay, maybe I can show here. Yes, so here you have an output of a layer of neuron, and normally what you do is that you have one wire for each neuron, right? That goes to the synapse. But here, what we do instead is that we sum these microwave powers, and so through a single wire, we can send them to all the synapses. The same signal to all the synapses through one wire. And this really, I think, simplifies the connection scheme. And we can do that through one wire because we use this frequency multiplexing. So this one talks to this one, and there are no interference. You see what I mean?
Yeah. So it vastly increases the efficiency of being able to analyze a signal with a certain number of devices. Yeah. No,
yes. So it will be only one wire to carry. So we have estimated that we can carry about 500 signals on one wire. So so it's connectivity of at least 500 synapses per neuron, and there are ways to increase that. So and all this fully in parallel. So that's.
Oh, great, thank you.
Thank you for this as well. I'm also scanning for any possible questions. We have one from Runze. Just before that, if I may, Julie, I guess, how much of a driver what you're doing is the endurance that Spintronics can bring, in the sense that a lot of amazing things are being demonstrated with competing technologies. Yeah. In this case, in Spintronics, you don't have recrystallization processes, or atoms moving, things like that. So I guess this adds to the endurance. I don't know if you've calculated it or you estimated for the specific context of multiply and accumulate operation, but how much is endurance one of your drivers or one of your sort of things that you...
Yes, it's a very good question. No, I didn't calculate. So so here's something that I didn't mention, is that, well, I talked about it, but the weight of the synapse is the resonant frequency of the synapse. So if we want to have plastic synapse, we need to be able to tune this resonant frequency. And so, well, it's not written here, but because we have two magnetic layers, so for example, here you can see we have two magnetic layers. So just by reversing the bottom magnetic layer, because of the stray field, the frequency values, okay? So if we do that, this is non-volatile, and this is going to be very high endurance. Only two states, and this is okay for many applications, not everything, but and we want to have multiple steps. We need to be able to tune the resonant frequency in a continuous way, and for that, probably we need to combine resistive switching. I mean, we need to use electrical control, magnetic anisotropy. And this, I don't know about the endurance of that. This has to be checked.
Okay, good, thank you. So we have another question from Runze Chen, another one for PhDs. I think part of it might have been answered. And Runze, if I don't represent the question well enough, feel free to jump in and directly ask it. So yeah, thanks for the talk. Two questions for the synapses. Are they non-volatile? I think you already indicated something about that. So, and the other question is, how does the huge network interconnect between layers? How do you interconnect between the layers?
Right, so what we would do, so here, for example, if you start by sending RF signals, if the RF signal you want to classify, you send them to the synaptic chains, okay? Then you have the DC voltage, and basically you amplify it and you send them to a neuron. And then you have the output of the neurons here. And then what you do here is not written, but you sum them, amplify, and send to the other chains of synapses, and so on and so forth. And so it's a bit strange because normally it's not in neural network. You have all these synapses are connected, in diagonal, etc. So here the arrangement is a bit different, but this is how it looks. And you see, because we don't have all these wires that interconnect, and you have only like lines like that, you already guess that it's a simpler architecture.
Okay, thank you very much. Let me check if we have any other questions. In the meantime, I do have one. We do have an indication of the ratio between number of synapses, number of neurons in the brain. So in that sense, we know what we can aspire to, and we do have a feeling about existing and competing technologies. So with this approach, is there any way to estimate an upper bound on this ratio, or where does this place us in how much synapses per neuron we can have?
Yes, so basically a bound is put by how many frequencies you can have for the synapse. you know, the frequency range and the damping, because this is what defines the width of this response.
Mm-hmm.
So, I have estimated that we can have about 500 synapses per neuron in that way, but then we can increase this number by connecting different chains together. So I think we can reach over 1,000.
Over 1,000. Okay, it's certainly very, very impressive. Is there any hand that I'm missing, or someone who sent a message and I didn't see it, or any follow-up questions? So obviously, you know, one of the main drivers for doing that is to sort of converting it into technology. So if I were to ask you to estimate of the time frame where, you know, if things go well, this could be, how close or far are we from converting it to technology, especially since the MTJs are already very sort of industry compatible. And a sub question to that, a bit naive perhaps, but okay, you depict something that has neurons and synapses, and the strength of it is this RF sort of mediated deep learning. Do you see this becoming sort of an all or nothing, or do you see it as sort of Spintronics first offering synapses and then the neurons? Or could it be that first, as a component, you might see something like synapses breaking through established technologies?
It's a difficult question. I don't think anyone has really an answer to at least to your last question. It's very difficult to say, you know, if one kind of device can emerge by itself, or yes, it could be that you have CMOS neurons and then magnetic synapses going with them. It's completely possible. It's very difficult to say, because of course, when you want to go to a product, you have the question of cost and all the what is really the application, what is the application behind, and this is not clear. Something people are trying to figure out. Well, of course, one of the interesting application of neuromorphic computing is embedded AI, but then it's not clear yet why you want embedded AI, and should it be only for inference or be trained, or it's not clear. Then regarding our specific scheme with RFs, I think one thing we need to demonstrate. So, okay, magnetic tunnel junctions can be integrated in CMOS, but there has not been yet a demonstration of them being integrated in RF CMOS circuits, are designed differently. And so now we have started to collaborate with colleagues who do this kind of RF circuits, and we want to demonstrate the compatibility and communication in that way. Basically, we want to make the RF CMOS building blocks that will help interconnect these things together. Okay, excellent. Obviously, as you said, because you depart from an experimental physics viewpoint, I think it is clear that you show things step by step, but also that at each step you need to sort of curate the data and handpick the rules. So I guess you see, so at which point do you really need to, or perhaps you already started tailoring the algorithms and the networks with the hardware at the same time? So would it be some sort of generic hardware that can run existing approaches, or do you need to tailor the neural network to the hardware as much as the hardware to the neural network? Yes, it's something you need to co-design, and this is one of the challenges, but also one of the things that are really interesting, right? So, and one of my dreams, goal is to use as much of the physics of the elements to implement the training. So ideally, we would like to have a network that computes the gradients through its own physics.
Fruition physics. Okay, so
That would be really
it's very, very impressive. Shall I check again? Maybe people can help me. Is there any hand that is raised or any follow-up questions that I regretfully missed? Or is anybody having another question? I think we don't have any questions at the moment. I'm sure I speak on behalf of everybody, thanking you for finding the time. It's very, very, it's not only bio-inspiring, it's also very inspiring for us. And yeah, I think let's have a round of applause and thanks for Julie. Thank you very much.
Thank you very much for your attention and for the questions and everything. So.
Okay, thank you very much. Thank you. Thank you.
Well, thank you. Bye-bye.
Bye.
Thank you, Julia.
Bye.
Bye.